Let's start with the second and last part of the reduction-oxidation reaction. Here we have a very complete example, which you can use as a reference in all the redox exercises that you're going to do. The exercise is the following. In oxidizing media, chromium is in aqueous phase as chromate, while in relatively strong reducing mediums can change to chromium 3. Knowing that the standard reduction potential of the pair is 1.48 volts in basic medium A. Write the reduction half reaction. B. Chromium 3 cation forms in the presence of hydroxide ions, a very little soluble solid, chromium hydroxide. Write the reduction half reaction of the chromate, which gives as a product the solid formation. C. Knowing that the constant of the solubility product of the chromium hydroxide is 10 to the power of minus 30, what will be standard potential of the half reaction of section B? D. If we have a water at pH equals 8 contaminated with chromate with a concentration of 10 to the power of minus 5 molar, at which potential values the chromium begins to reduce and precipitate as a chromium hydroxide? You will usually have to read all the exercises 2 or 3 times to understand them perfectly. In this case, they mention that in an oxidant medium, chromium is found as chromate, and in a reductor medium, found as chromium 3 cation. They give us the standard reduction potential for the pair of chromate and chromium in basic medium. Let's start with section A. To write the half reaction equation, we first put chromate to the left and chromium 3 cation to the right. We have to equal the reaction. Even though it's in basic medium, we will equal them first in acid medium and then switch to basic medium, adding the water equilibrium the necessary times. We have 4 oxygens to the left and none to the right. So we add 4 waters to the right part to equalize them. Now we have 8 hydrogens to the right due to the water molecules. So we add 8 hydrogens to other side. The half reaction is already equaled. In the left, we have 6 positive charges, and in the right, 3 positive charges. So we have to add 3 electrons to the left part to equalize the charge both sides. Therefore, the number of exchanged electrons is 3. To switch to basic medium, we use the water equilibrium. We add as many equations as hydrogens there are in acid medium equation. Here, the goal is to get rid of the hydrogens, having hydroxides instead. The equal reaction in basic medium is the one you can see in the slide. Let's do section B. Now, we are told that the chromium 3 cation forms a very insoluble solid in the presence of OH anions, chromium hydroxide, and we have to give the reduction half reaction of the chromate, which gives us the solid mentioned. We first write the chromate to the left and the chromium hydroxide to the right. We start equalizing the reaction in acid medium. On the left, we have 4 oxygens and only 3 on the right. So we must add 1 water molecule to the right. Now, in the right part, we have a total of 5 hydrogens, 3 from the hydroxides and 2 from the water molecule. So we must add 5 to left to equalize them. Lastly, we switch to basic medium, and to do so and get rid of the hydrogens, we add 5 water equilibriums. Lastly, we simplify and we get the reaction you can see on the slide. Let's move to section C. Knowing the solubility product of chromium hydrogen, we must calculate the standard potential of the half reaction that we've just equaled. What information do we have? The first equation is the one of the solubility product. The constant equals 10 to the power of minus 30, and the logarithm of the constant is minus 30. From the chromate equation, we only know the standard potential given by the problem's introduction. Finally, we have the water equation with the already known constant. Now what do we have to do? We need to calculate all the constant logarithms. To do so, in the second equation using Nernst's equation in standard conditions, the standard potential is 0.059 divided by the number of electrons exchanged multiplied by the logarithm of the constant. The number of exchanged electrons is 3. And now we can already isolate the value of the logarithm of the constant, which is 75.25. The next step is to do a linear combination with the previous equations to get the one we are looking for. In this case, if we try it, we can see that we have to subtract the first equation to the second one to get it. In other words, we have to add the second equation and the first one, with reactants and products switched. Now we have to reorder the equation, simplifying the chromium cation, which is found on both sides, and with this we obtain the equation we were asked. To find the value of the constant, we have to do the same operation, reaction 2 minus 1, but with the logarithm of the constants. Therefore, we do 75.25 minus negative 30, which gives us 115.25. Once we have the logarithm of the constant, the last step is to use the Nernst equation again to find the standard potential. In this case, we know the logarithm of the problem constant and the number of electrons exchanged, 3, and we obtain the standard potential, which is 2.07 volts. Lastly, let's solve the last part of the problem. We have water at a pH of 8, slightly basic, contaminated with chromate at a concentration of 10 to the power of minus 5. What is the potential value so that the chromate starts to precipitate? First, we write the problem equation and Nernst's equation. We are asked for the potential of the equation under the problem's conditions. The Q has the same expression as K, the constant of the reaction, but the concentrations are different. The Q is the value of the hydroxide concentration to the power of 5 divided by the chromate concentration. Water and electrons are not taken into consideration. We don't include chromium hydroxide either, as it's a solid and has an activity of 1. Substituting the concentrations given by the introduction of the problem, the result is 2,56 volts.